Okay, we will go through some important points in the class 11 physics chapter 8 mechanical properties of solids. Okay, so what is deforming? Deform means there will be a change in the shape or size of the material. Okay, what is elastic and plastic? The tends to regain its original shape and size when the applied force is removed. Then it is called elasticity, and the deformation cause is known as elastic deformation. Okay, tends to regain its original shape, that is elasticity. Plastic means other way. Substance called plastic. Okay, there are no cross tendency to regain. Okay, it won't regain its original shape or size. Okay, that is the plastic. So elastic and plastic difference. Stress and strain. When a body is subjected to deforming force, a restoring force is developed in the body. That is restoring force. This restoring force is equal to the magnet but opposite direction to the applied force. This restoring force per unit area is called stress. Okay, restoring force per unit area, force by unit area. Force is unit Newton, area is meter square. So Newton per meter square. Okay, or Pascal. This is the stress, unit of stress. Okay, this tensile or compressive stress can also be termed as longitudinal stress. Okay, this is the longitudinal strain, delta L. Change in length divided by the original length is a longitudinal strain. Longitudinal strain, delta L by original length. Okay, there is a shearing stress also. Shearing stress is the displacement, okay, delta x divided by the original length. Tan theta. Angular displacement theta is very small. Then there is hydraulic compression. See, this is the longitudinal strain. Okay, tensile stress. Okay, this is the shearing stress. The angle theta, tan theta equal to delta x by this L. Shearing stress. How we apply a shearing stress? This is the volumetric. Okay, you are applying force in all directions. Hydraulic compression. Volumetric strain equal delta V, change in volume divided by the original volume. So now you understand what is this longitudinal strain and the shearing strain and the volumetric strain. There are three types. Okay. Volumetric strain, delta V by V. Hooke's law, that is stress is directly proportional to the strain. This law is applicable only in the linear portion of the stress strain curve. Okay, stress strain curve. Only in this linear portion this Hooke's law is applicable, not in these portions. This is the yield point. The stress corresponding to this point is yield strength. Yield point, yield strength. Okay, this curve is not applicable. Hooke's law is not applicable for this type of curve, non-linear. Okay, these are called elastomers. They don't obey the Hooke's law. Hooke's law. does not obey Hooke's law. Most of the elastomers. Young's modulus ratio in stress and strain. Okay, stress is force by area, strain is change in length divided by the original length. More Y means the strength of the material is more stronger the material. Okay, these are the Young's modulus of some of the materials. Okay, for example, steel. Okay, this is why steel is preferred than for a heavy duty machines. What is elongation? Okay, delta L, that is the elongation. Okay, delta L by L is strain, but delta L elongation. Strain delta L by L. Okay. Now the important here the ratio between this how the Young's modulus is related to the change in length. See here was inversely propose Young's modulus and the change in the length. Copper above, here copper below. Steel below here, steel is in the above here. That is why it is important, the ratio. This is the mass and weight. Weight equal to mass into the gravity. Shear modulus G. Shearing stress divided by shearing strain. These are the shearing model of some of the materials. This is the displacement. Okay. Bulk modulus. This is the ratio of the hydraulic stress to the corresponding hydraulic strain. That is the volumetric strain. Bulk modulus B equal to pressure into change in volume. P is the pressure, B is the bulk modulus. Compressibility is the inverse of the bulk modulus. 1 by B is the compressibility, that is K. This is the bulk modulus sum of the, for example, class. Okay, 37. This is the density of the water. 1000 kilogram per meter cube. Okay, that is the density of the water, rho. Fractional compression delta V by V. Poisson's ratio. This is the elastic potential energy. So you have to integrate 0 to L YAL divided by, so if you integrate, then this will become with respect to DL, then the L square by 2, 1 by 2 if you take out, then it will come. Okay, half into stress into strain into volume of the wire. This is the volume, strain, okay. This is the Young's modulus. Of this is stress and strain. So how much the area of cross section of the rope should be for this? Okay. Stress is the restoring force per unit area. Strain is the fractional change in the diamond. Hooke's law. Some of them they does not obey Hooke's law. That is elastomers. Volume strain. Okay, you can go through these points. Okay. Okay, we will go through the exercise. A steel wire of length 4.7 meter and the cross sectional area stretches by the same amount as the copper wire of this length cross sectional area under the given load. Okay, the load is same and stretches the same length. What is the ratio of the Young's modulus of the steel to that of the copper? Okay, the load is same, change in the stretches the same amount. Okay, stretches by the same amount. Okay, these are all given: length, steel, copper, then the area of the cross sections is given. Delta L equal for the thing and force also equal for the same load. Okay, Young's modulus equal to force by area divided by the change in length. Okay, now they are asking the ratio and they are saying the same load and the same stretch, that is change in length also same, that is delta L and force will cancel out. So after that you will get, look at this, length of the steel here, area of cross section of the copper, area of the steel, length of this ulta is coming here, ratio of the Young's modulus of steel to the Young's modulus of the copper. Okay, so is directly proportional, Young's modulus directly proportional to the length, inversely proportional to the area of cross section. So after that you will get this. Figure 8.9 show the stress strain curve for the given material. What is the Young's modulus? B. Approximate yield strength. Okay, this is given in the page 4. This is the Young's modulus, stress to the strain. Okay. Young's modulus, stress by strain. Stress, if you take at 150, then strain is 0.002. 150, here strain, this is the strain 0.002. So this is the Young's modulus. The yield strength is 300. Okay. Maximum in the elastic region. Yield strength. This is the 300. This is the elastic region. That is the linear region. So this is the maximum. This is the yield strength. The stress corresponding this point is the yield strength. So here this is the yield point, corresponding to this is the yield strength. Yield strength. Okay. The stress strain group for the material A and B is given. Which of the material given as the greater Young's modulus? The slope is more for the stress by strain. The slope will be more for this. Looking at this itself, we can make out. Slope is more for this. So Young's modulus will be more for this curve. Okay. Which of the two stronger material? So more Young's modulus means more stronger. Slope of A is greater than slope of, so A is a greater Young's modulus. A require greater force to produce same strain. So produce this strain. So A is stronger. More Y means more stronger. Read the following two statements. State the reasons. It's true or false. The Young's modulus of the rubber is no. A rubber you can easily strain. So the Young's modulus of the rubber is greater than that of steel. Then that is false. Steel has the higher Young's modulus. Stretching of the coil is determined by the shear modulus. Yes, shear modulus. So stretching of the coil changes only the shape. It doesn't change the dimensions. That is a length or volume. It only changes the shape. So this is shear modulus. Two wires of diameter, one made up of the steel, other made up of brass. Steel and brass are loaded as shown in the figure. The unloaded length of the 1.5 meter. Okay. So here the important thing is that for the steel the load is 4 kg plus 6 kg. So this is 10 kg. Okay. For this steel. But for this portion brass is only 6 kg. That is important here. Okay. So they compute the delta L, that is the elongation of the steel and brass. Young's model force by area delta by L. Area pi r square. R radius is diameter by 2. So from this we can find the delta L for the brass. And same way this is the delta L for the steel. Elongation they are asking for the steel and the brass. The edge of an aluminium cube 10 centimeter long. One piece of the cube is firmly fixed in a vertical wall. The mass of the 100 kg is then stretched in the opposite face of the cube. The shear modulus of aluminium is given. What is the vertical deflection? Okay, see the different words they are using: vertical deflection, elongation, compressive strain, elastic deformation. So you have to understand maximum load the cable. So these things you should understand. Shear modulus equal to shear stress area by shear strain. Okay, force by area A equal to this is in meter. Okay, so the delta L, the point 1 is 10 centimeter. Okay, this is given. Okay, shear modulus is given 25 GP. This is given shear modulus. Okay, four identical hollow cylindrical columns of the steel support along. This is the mass. There are four pillars. The inner and outer radius, okay, 30 and 60 centimeter. Assume the load distribution to be uniform. Calculate the compression strain. Okay, delta L by L. Okay, compression strain delta L by L we have to find out. Area, this is the outer minus inner radius. Outer 6.6 meter, that is 60 centimeter. This is the load, mass into G, gravitational force on the four columns. This is the total force. So divided 4 force on the each column. Stress equal to force by area. Force on the each column divided by this is stress. Young's modulus equal to stress by strain. For the steel, this is the Young's modulus. This is from the book. So strain we can. This is the strain delta L by L. A piece of copper having a rectangular cross section is pulled in with this force, producing an elastic deformation. Calculate the resulting strain. Stress by strain. Strain equal to stress by Young's modulus. This is the Young's modulus of the copper. Okay, this is the area of cross section. So strain, we can compute the strain. A steel cable of the radius supports sky area of a maximum stress. So not to exceed this much. What is the maximum load? See radius in meters, stress force by area. So the maximum load force is equal to stress into area. Stress pi r square is the area. So this is the maximum load. A rigid core of mass 15 kg is supported symmetrically by three wires, of which 2 meter long. Those at each end of the each rod are the copper, and the middle one is iron. Determine the ratios of these diameters of the each of these to have the same tension. Okay, this is the diameter because d by 2 whole square, pi r square, d diameter by 2 whole square, then here 4 will come, d square by 4, that will 4 go up, then d square will be down. So d equal to square root of 4 by strain will come. So they are asking the ratio iron to copper, then this force will cancel out, then the Young's modulus of copper by iron. So this is 1 is to 1.25. A 14.5 kg mass fastened to the one of the steel wire is unstretched. Okay, and calculate the elongation. Here delta L only they are asking. The Young's modulus of steel is given in this table. Okay. See here, these are the various Young's modulus of various materials. This is the revolutions per second into radians per second. Okay, 2 pi radians. 2 into 2 pi area total F. So this is the formula they are using. Okay, mg into m omega square into L. Mass, gravity, mass, this is angular velocity omega. Okay, this is the length. So after that delta L, this is elongation. Compute the bulk modulus of water from the following data: initial volume, pressure increase, okay, final volume, explain in the simple terms why the ratio water air is more compressible than the water. 8.12. Initial volume, final volume, difference in volume. Okay, 1 liter equal to 0.001 cubic meter, that is 1 into 10 power minus 3 meter cube. This is the 1 liter equal to this cubic meters. Pressure, your ATM to Pascal they are converting. Okay, bulk modulus equal to pressure by change in volume, delta V by V. Pressure, this is the change in volume. So change in volume, this V will, original volume will go up. Okay, this is the bulk modulus. Bulk modulus of air is this much. So air is more compressible than the water. Okay, this ratio I means air is more compressible than the water. What is the density of water at the depth where the pressure is this much? Given the density at the surface, okay. Compressibility is the 1 by bulk modulus. Compressibility is 1 by bulk modulus. Pressure at 8 atmospheric pressure. This is converting into Pascal. Water density at the surface they have given. Density at the depth we have to find out. Assume volume at the surface volume. This is the volume. Mass by volume equal to density. So volume is mass by density. Okay, change in volume. Mass by density. Initial minus final. Volumetric strain delta V by original V. Delta V is this much. Original is mass by volume. This is denominator is coming go to when you take up then it will become ulta density by mass. So when you simplify this you will get 1 minus rho 1 by rho 2. Bulk modulus equal to pressure into initial volume by the change in volume. Okay, pressure by bulk modulus equal to delta V by V. So 1 by B is compressibility. So this is the compressibility of water. The pressure is given. So after equating this you will get this. Density at the depth of at this pressure. Compute the fractional change in volume, that is delta V by V. They are asking of the class tab when subjected to the hydraulic pressure. So hydraulic means this is a volumetric strain. P is given pressure, so we are converting into Pascal. Volumetric strain delta V by V equal to P by bulk modulus. P is given bulk modulus. Bulk modulus of the glass. Okay, the delta V by V we find out. Determine the volume contraction of the solid copper cube. 10 centimeter is the one side. When subjected to the hydraulic pressure, delta V they are asking, delta V. This is in meter. This is given bulk modulus of the copper. Volume is a length cube. Okay, after substituting this you will get the delta V. How much should the pressure of liter water be changed to compress by this much percent? Compression 0.1%, 0.1 by 100 into volume 1 liter. Okay, fractional change. Okay, this is delta V by 10 power minus 3. Bulk modulus pressure by change in volume. Pressure equal to bulk modulus into change in volume. B of water they given. B of water is this much. So P equal to this is the pressure. We have to apply this much pressure. Okay.